Welcome everybody to Space of UT. Oh, okay. I guess you're gonna double see me here, my screen and
Make sure you can hear it.
yeah. First Space of UT seminar. Thank you so much for Dr. Sam Kenyon here for breaking the ice. We've been struggling a little bit to get somebody, but now actually I think we're gonna almost be completely full for the rest of the semester.
Good.
Yeah. So there's a couple I haven't heard confirmations from, but yeah, I think we should be pretty good. And yeah, if you have a presentation, some kind of topic you want to talk about, feel free to email me. Really, it doesn't have to be something super polished or even super technical. I go back to, and I was realizing kind of going back in history, it was the second seminar we ever did, was actually something not technical at all. It was more talking about the policy about like radio astronomy, like optical astronomy kind of thing, and what happens with being able to do that with proliferation of like SpaceX and all the satellites, that kind of thing, and what happens to radio astronomy, like what happens to Green Bank, that kind of thing, when you have tons of objects flying overhead making RF noise. So anyway, so it's not like not a very technical paper. There's more thinking about that philosophy of like what's the regulation, how do we do that from the space related stuff. So a neat topic. So yeah. Without further ado, though, we have Dr. Sam Kenyon here today on some space instrumentation and things that you've been looking.
Yeah. Thanks, Kevin. Hi, everyone. Thanks for those who have come in person and for those who are calling in online. I'm giving a seminar for the Aerospace and Ocean Engineering Department on Friday morning, and so this will be just the technical portion of that discussion. In that seminar, I'm going to talk about some of like the future work and research projects that I want to do in the future. But today I'm just going to be talking to you all about two programs in particular that I've been able to work on, and one being here at Virginia Tech, along with some folks who are on the call here, Dr. Harding and Nicholas Jones. Hi, you guys. Yeah, just excited to kind of share some of those programs. And yeah, so we'll get started here. Just a little bit about me. I did graduate school at the University of Florida in the Precision Space Systems Laboratory, or PSSL. I worked a bit on some hardware development for CLIC. It's a Cube satellite mission that involves laser communication. You can see a graphic of that mission here. And then also worked on the Laser Interferometer Space Antenna mission, or LISA, that's going to be launched in the early 2030s. Worked on hardware development and some dynamics modeling of some of the sensors in that system, which you'll get to hear about in this talk. In the summer of 2019, I was an intern at Ames Research Center, NASA Ames, out in the Bay Area of California. And while there, I worked a bit on some microfluidics experiments on a potential Europa lander mission, looking at electrochemical tests that can be done, and as well as the microfluidic optical, not optical, but fluids benches to kind of do those tests. To work on that summer. And then since the fall of 2021, I've been here at Virginia Tech as a research associate. And I've had the opportunity to work on a number of different projects and missions with lots of different faculty here. I've been able to work on hardware for COSY, the Compton Spectrometer Imager, that's to detect gamma rays. Is going to be launched towards the end of this decade, as well as the student-led UT-ProSat mission, the hopeful 6U heliophysics mission, which I'm going to be talking about that project as well in this presentation, and then also been doing a bit with satellite communication and networking, which Jack has been involved in here. Okay, so just a brief definition of technology readiness level, if this is something that you haven't ever heard of, seen about, just going to define this here. This is often used in technology development, especially for space programs, to measure, it's a measurement system that's used to assess the maturity level of a particular technology. So starting from the red being beginning technology, moving through to green to be advanced technology, goes from 0, 1 to 9. So technology readiness level 1, 2, and 3 are often what's done in a laboratory environment, proof of concept. TRL1, I think the deliverable is just having a paper that you're able to describe what your concept is, and that it's possible to do so. And then at TRL3, you kind of have this proof of concept where you're able to do some sort of test to kind of prove that your system, whatever your technology is, could work. From TRL 4 to 6 is really where the proof of concept and the design of an instrument or a component is developed. And this is done through functional verification and creating a breadboard, and then moving that breadboard design that works in the lab and starting to think about what environments it's going to need to work in and to make sure it works in those environments. And then TRL 7 to 9 is kind of the final stages where you're able to actually do demonstrations in relevant environments and do some tests and actually get to fly the technology. With TRL 9 being the last level of this has flown, and we verified that this works well in the relevant environment for the relevant mission. And that's kind of the span from conception, TRL 1 to TRL 9. It's flown, it's verified. So academia and research labs, like you'd see at Virginia Tech, has a really unique role to play in the beginning TRL stages up through TRL 5. To be able to develop new concepts and instruments and then move them through technology readiness levels to the point where we can convince sponsors or perhaps interested parties that the sensor or the technology is indeed worth investing in and has a lot of potential. Right around TRL 4, when the proof of concept starts to become materialized in a breadboard environment and starts to be developed for a relevant environment, this is where academia and research institutions like other national labs can partner with industry companies, whether that's large companies or even smaller companies that do specific things to kind of help design the components and make them from the breadboard stage up to the prototype stage, what it would look like on flight. And then once things get to TRL 6, often at this point, a company may take the lead of a particular technology with academic support, but this can look different depending on what the technology is. So if it's something that's really specific to a science mission, oftentimes academics will stay involved. But this is kind of the stage where it's where industry can get more involved, or small businesses, things like that. So right in this TRL 7 to 9 range is where you have a flight opportunity, where if you're able to validate that a design meets TRL 6 and demonstrates well in a relevant environment through whatever ground testing you can do, to get to the more advanced TRLs, you have to do some sort of a flight mission to kind of get it to that rating scale. So with this in mind, we'll be looking at two main programs of kind of seeing how the technology development has evolved in an academic lab environment for meeting these milestones and developing technology to be able to fly and be relevant for science missions. So the first topic to address is going to be talking about precision space inertial sensors. Defining what they are, how they use them, specifically diving into what work was done in developing them for the LISA mission. So what is a precision inertial sensor as I've defined here? This can be a gyroscope or an accelerometer that's is composed of like a free-floating test mass, as you see here. And if you can precisely measure the orientation and the translation of this test mass over time, you can back out really accurately the spacecraft attitude and relative position from that. These types of sensors are typically composed of a test mass that's in this free fall or near free fall condition, right? They're free floating in 0 Gs of space. And typically they're surrounded by capacitive electrode housing. So the surface of the test mass and the surrounding housing forms a capacitor. And you can use the capacitance measurement to back out what the distance measurement is really precisely. So that's what makes these free-floating test mass sensors really helpful for space applications for inertial sensing. So this type of concept of a sensor has been used on a number of missions before. The most common that you may have heard of before are the number of Earth geodesy measurement missions that have been launched over the last 20 plus years to measure the gravity distribution of the Earth, which is really helpful for Earth science, climate studies, lots of things like that. So CHAMP was the first one of these missions to fly to kind of be able to do accurate gravity measurements across the surface of the Earth. Followed by GRACE, which I'm guessing some of you have heard of, this was a two spacecraft orientation that measured the distribution of mass on the Earth, like where there's mountainous regions or over the ocean. There's a lot of studies done on like the polar ice caps and the rate at which they're melting by seeing the mass distribution over the course of some years. So I believe around 2017, GRACE, the mission was ended, which was an extended 2 years past its 2015 nominal mission deadline. GRACE follow-on was launched in 2018 to be able to provide continuous data for the Earth science community. There's also GOCHI, which is the European Space Agency equivalent of GRACE, which was launched in 2009. It's also the microscope mission. So this is departing from Earth geodesy measurements. You can use this type of sensing to measure gravity really precisely and do verifications of general and special relativity. So that's what was done in the microscope mission that European Space Agency launched in 2016, which a picture of that's here. As well as the Gravity Probe B mission back in 2004 was launched to test the equivalence principle. And the last application of these sensors that have been seen in the past is done for gravitational wave measurements, which these precision inertial sensors had flown on LISA Pathfinder, which was a mission that flew from 2015 to 2017 to validate if the technology proposed for LISA would perform at the levels necessary to detect gravitational waves. And that was the sensor on board looked very similar to all of these sensors. So I'm going to talk more specifically about the sensor applied to gravitational wave measurements, but you can see here that this sensor technology can be applied for a lot of different applications in which you want to really precisely be able to measure the effects of gravity and consequently the effects that aren't due to gravity. Okay, so these sensors can enable something called drag-free motion. And so the goal of these inertial sensors is to measure the spatial and temporal variations of the gravitational force. So basically, what force of gravity is something experiencing at any point in time? And the way that that works is it is able to measure non-gravitational forces really accurately because oftentimes the non-gravitational forces affect the whole spacecraft body, whereas the test mass is shielded from a lot of those disturbances, things like atmospheric drag that the spacecraft body experiences, but the free-floating test mass contained inside would not, as well as solar radiation pressure, another external force other than gravity that a spacecraft might experience that the test mass shielded would not. And so basically, the test mass is moving only due to gravitational forces, whereas the spacecraft is moving for all these other forces that we see in the system. So to compensate for this and enables this drag-free, or otherwise known as purely gravitational motion of a spacecraft, where it follows the free-floating test mass and is shielded from all non-gravitational forces by basically compensating for the motion of the spacecraft by basically trying to keep the test mass centered. You kind of see that as the spacecraft is moving around the test mass, it can use its own thrusting mechanisms to keep itself centered on the test mass to be able to basically cancel out the effect of all these non-gravitational forces. So I mentioned a lot of these missions already. You can kind of see here what the relative acceleration noise levels are for the missions that I've mentioned. If you wanted to bring the fidelity like less than grace, but you didn't want to have a free-floating test mass, there's some micro electromechanical systems that you can have onboard chips that do inertial sensing through miniature electronics and optics, and having crystal oscillators and things like that to do the measurement. But this is only really able to measure things in the micrometers per second squared range. And then you have a jump down to the type of things that grace can do here, as seen in this graph. The root hertz here is just taking the amplitude spectral density of the acceleration. So basically, this means that the accuracy of your sensor is dependent on the frequency of the signal that it's experiencing. So you can kind of see all the way down to microscope mission. A grounding wire was used to discharge the test mass, which I'll get into in a moment. And you can kind of see that there's a separation of accuracy of dealing with contact-free methods, as seen in LISA and LISA Pathfinder. Okay. It's muted. Okay, so what is the LISA mission? It is to detect gravitational waves in space, which gravitational waves are disruptions or ripples in space-time that propagate out from big astronomical events that happen, like two black holes or two really massive objects merging together into one. The mass isn't conserved in that event that astronomers were able to find. And that was due to a percentage of the energy kind of being lost in the system through these ripples in space-time gravitational waves. We have ground-based observatory that detects gravitational waves at much higher frequencies, but a space-based observatory is needed to measure gravitational waves in these lower frequency ranges. It's composed of 3 spacecraft that are drag-free in that equilateral triangle formation you just saw. And each spacecraft is equipped with 2 telescopes to be able to do laser interferometry between its neighbors. And each of the spacecrafts are 2.5 million kilometers apart, which, if successful, would be the largest instrument that humans have ever built, which is pretty cool. And so you can see the interferometry is composed of this large telescope, an optical bench, and at the heart of it is the gravitational reference sensor, this inertial sensor that I've previously defined. Oops, I was hoping to skip ahead in the video to where it talks about. Oh, well, there's a picture of it on the next slide. So at the heart of the LISA spacecraft is a gravitational reference sensor, which is composed of this free-floating test mass, which you see here. It not only acts as the position anchor, as I've described in drag-free control, but it's also the endpoint for the interferometer. So you can see this red signal coming in. That's actually the endpoint in the sensitive direction for the interferometry measurement. It's composed of a gold-platinum alloy, which is dense and non-magnetic, which helps with some of suppressing some of the noise. And it's also shielded from disturbances through its housing. And its housing is composed of these capacitance electrodes, which you can see the schema for LISA here, which is quite advanced compared to some of the other sensors. The fact that you have 2 electrodes per side means that you also can have precision in terms of the orientation of the test mass. If you only have 1 electrode per side, then you can only back out the average distance. So at least 2 is necessary to kind of get that orientation. And the way that this works is through Coulomb's law for capacitance. The capacitance is equal to the charge divided by the voltage that an object experiences, which is a function of the surface area of the 2 plates, as well as the distance between them and the existing electric field. Or this is actually the permittivity of free space. So these different electrodes have different functions. There's some that are used for sensing and actuation, which are the green ones, and then some that are used to actually inject a signal if need be. Say if the test mass needs to stop science mode and its position needs to be corrected, use those electrodes for that. Everything's coated in gold for homogeneous electrostatics purposes and makes a really nice reflection surface for the interferometer. Okay, so charge management system. Basically, radiation effects aren't perfectly shielded from the test mass due to the spacecraft body being surrounding it. A lot of the radiation that's due to primarily solar radiation pressure, so that's radiation coming from the sun, and cosmic ray particles, which is radiation that comes from distant galaxies that eventually finds its way to our solar system. A lot of the spacecraft shields the test mass from this, but some of the radiation will eventually pass through and land on the test mass. So this charge of the test mass, if left over time and not touched and not grounded, right, because it's free floating, in the presence of an electric field, will actually start to move due to that electric field. So this is not very good, right, because we want to measure, basically have the test mass be following a purely gravitational orbit. And if it's moving due to things like the charge buildup, then we're kind of diverging away from this purely gravitational orbit. So the charge building up not only has this Coulomb force, as I've described here, but also a Lorentz force, a magnetic field, which for the purposes of LISA is negligible. And you can actually design your system to allow for the Lorentz forces to be negligible if it's made with that non-magnetic material, the gold platinum alloy that I mentioned. And then it's kind of also encased in a housing that also acts as a pseudo Faraday cage. So the Coulomb force, the force from these electric fields is equal to the charge Q times the existing electric field E. And if we take this equation in the sensitive x-hat direction, which is the direction of the interferometry, we're left with the following equation. Now, if each component, both the charge of the test mass and the electric fields, not only have a DC component, which is denoted by this not subscript, that is left to grow over time, it also has this delta term that is dependent on time. And so what happens is when you combine these all into the Coulomb law equation, what we really care about are these two terms where we have varying forces that are dependent on time and vary in the frequency band that the LISA measurement cares about, multiplied by DC forces that, if left over time, will allow them to grow. We actually get large in-band frequency contributions of these signals, and that is bad for our mission. So basically, if there's an noisy electric field, which exists inside of the spacecraft because there's other electronics and there's other things going on that have this time-varying electric field, and the charge is left to grow over time, then this term circled in green will eventually grow and be large and influence our precision of the science measurement. So for LISA, this happens at potentials at about plus or minus 70 millivolts. So the net charge of the test mass compared to the spacecraft ground. Once it exceeds 70 or minus 70 millivolts, then the charge needs to be controlled and brought back down to 0. So on other missions, like in GRACE and Microscope, a grounding wire was used, as I mentioned before. So this grounding wire is able to allow for a physical discharge of the charge buildup. However, this causes a dampening force, which limits the accuracy of these sensors. So this damping force, especially for LISA, is too high in order for LISA to make its noise performance necessary to detect gravitational waves. So another method has been exploited, which is using the effect of the properties of light, the particle nature of light through the photoelectric effect. So basically, the concept is you shine light onto the test mass, and if the work function of the metallic surfaces is less than the photon energy of your light source, then you can actually eject electrons from your source. So for our gold-coated surface, this happens at deep UV wavelengths, less than 289 nanometers. So if we can have a light source that's less than that wavelength, we can effectively move around electrons without having to touch it, without providing any force onto the system. Okay, so this concept did fly on LISA Pathfinder, but a much more abbreviated version of the photoelectric effect. And so it's desired to kind of understand how all these components come together to basically in order to know how this upgraded version will perform in space before launch, because we don't have the ability to test things in the space environment before the LISA mission launches. So extensive work was done in modeling and simulating the effect of charge on the test mass over time. And LISA Pathfinder data was used to kind of help inform a lot of these models that we developed. And as you see in this graph here, this is known as an apparent yield curve. It basically describes the rate of the test mass charge as a function of the UV light power and the test mass potential. So as the test mass potential increases, then the apparent yield based on an amount of UV power will also increase due to the presence of a stronger electric field, basically. And these apparent yield curves capture the geometry and surface properties and sensor capacitances within the GRS that kind of inform what the behavior is going to be. And so an analytical model was done and approximated in this linear region of these apparent yield curves, kind of between -1 to 1 volt of potential, since, as you recall, we can't go plus or minus above or below plus or minus 70 millivolts. So we have to kind of stay in this region in order to be in science mode. And this analytical model, you know, basically pulls data from these curves and combines it into this analytical model to describe the charge of the test mass as time passes. So the charge of the test mass as time passes is dependent on the environment. It's dependent on the internal geometries and surface properties that's captured here in the apparent yield curve. And basically, we can numerically integrate that equation of motion to understand how the charge changes over time. This is a breakdown of the model that was developed to basically describe the charge on the test mass over time. The analytical expression, unfortunately, could not be solved explicitly. At least I could not figure it out, even though I tried a number of calculus things to get the double numerical integration of the equation of motion into a useful form. So instead, a numerical model was developed, and you can numerically integrate in order to back out from all of these parameters that depend on what the charge of the test mass is over time to capture all of these things. So basically, this first term in the analytical model, it describes the charge of the test mass due to the apparent yield that was kind of backed out from those apparent yield curves you saw in the previous picture. And then this part is the environment and the noise of the environment, because there is not only does the radiation environment, you know, cause charge buildup, but it's not a consistent amount of buildup. So in one time step, you might have 5 particles build up on the test mass, and the next time step you might have 1 particle. And so that is a little bit of the noise associated with it, as well as this shot noise. So this is also the noise that you get from the light source, also having some variability of when the particles arrive. It's not always consistent based on each time step. So basically, for the environment and the noise of the environment, LISA Pathfinder data was used, which this was data that was published only a few years ago from the LISA Pathfinder mission. And the LISA Pathfinder mission was out in Lagrange point 1. So this radiation data is actually pretty useful if there's any desire to send another mission out there to see what the radiation effects are at Lagrange point 1. I don't think anyone's really dove into that, but that would be interesting to do. And so about a 14-day data run was done for this particular demonstration that I'm showing you. And once the time domain test mass potential was broken out, so basically seeing what the charge of the test mass was over time, the spectral densities were taken to understand what the influence of the force noise was in the frequency domain to see if it meets our requirements. So this was the result of the first step of the model. This is kind of showing the test mass potential, which you can relate to the charge through Coulomb's law over time, over the 14-day time span. And you can see based on the units on the y-axis that it remains below 3.5 millivolts over this 14-day time span, which is great, right? We can't exceed 70 millivolts. So we're kind of staying in a very close to zero range. And some phase and power amplitude noise was added to the UV light that's pulsed onto the sensor to perform this contact-free discharge. And basically, this pulse mode was kind of incorporated in this model. So next step of the model was to do the force response. So taking the spectral densities of this test mass potential over time and seeing how it performs compared to the requirement. So the requirement for the mission is seen in black, and the requirement for the for specifically the gravitational reference sensor is seen in the pink curve. So the pink curve is what our system has to make sure to stay below. And you can basically see the contributions of each of these elements seen in this model. The shot noise, which is the blue curve, remains below the limit of 5,000 electrons per second. It's at about 4,000 electrons per second of shot noise. This is due to using a low amount of UV power. It's about 2 nanowatts of pulsed UV light coming through. And then the red, yes, I'm moving my mouse and you can't see my mouse. So the red here is the effect of the existing electric fields, which is times the charge, which because the charge remains low throughout the 2 weeks, this stays quite low in terms of total noise. And the summation of the blue and red curves are seen in the yellow, which kind of tucks behind it. It's the summation of the blue leading up to this 10 to the minus 2 hertz, and then starts to take on the behavior from the red curve. So you can see that this remains well below the requirement of the noise limit from the GRS. And this is really helpful because this could potentially help us to do even better in our science measurements, having a lower noise floor, or we could afford to have higher noise in other subsystems of the spacecraft. Okay, so I've gone into some modeling work that was done for the LISA mission of understanding the gravitational reference sensor and the charge buildup on the sensor. Work was also done to validate the system through a ground-based testing apparatus known as a torsion pendulum. So this is a gravitational reference sensor experimental test bed in which there's a long, strong but thin tungsten fiber that has a very low torsional spring constant. And at the end of this very long fiber is a crossbar assembly. And at the end of the crossbars are the hollow test masses. And basically how this can basically emulate 0G in 1 degree of freedom is that because you have this tungsten fiber with a low torsional spring constant, as the torsion pendulum kind of rotates in this sensitive phi direction, the amount of spring constant is that the fiber experiences is really low. So it's essentially in free fall in that sensitive X, which you can see is perpendicular to the cross arms. And if you make measurements in that direction, you're in free fall in that 1 degree of freedom. Now in space, we're in free fall in all 3 degrees of freedom, but this is a really cool way to be in free fall on a ground-based test bed in 1 degree of freedom. So this is a CAD model of the torsion pendulum, and this is what's existing inside of it, the 4 test masses at the end of this crossbar assembly. Here's a picture of the torsion pendulum in this custom vacuum chamber that was developed. There's also this thermal room that was constructed around it to allow for passive temperature stabilization. Temperature effects over time added a lot of noise to the system. And so extensive work was done to kind of allow for temperature variations to be really low. So if you recall, we care about frequencies that are 1 hertz or less, or 0.1 hertz or less. which you think about the rate that temperatures change throughout the day, it would be very basically that rate of change of temperatures throughout a 24-hour cycle kind of hits that frequency range that we care about that's sensitive to the measurement. Okay, so part of the ground testing campaign was measuring the electric field potential in the gravitational reference sensor that was incorporated in the torsion pendulum to verify that a newer way to measure existing electric fields could be done on orbit to more speedily be able to measure the existing electric field. So if we look back at the equation that we cared about, right, we had this scalar DC, or this DC term of the electric field presence times the noisy charge. If we can keep the electric field amount that's biased to the test mass low, then we can suppress that part of the noise contribution. So for our purposes here, you can see this Coulomb law equation broken out. The electric field is a function of the capacitance of all the surfaces as well as the total capacitance, and this delta X, which is known as the electric field potential. And you can know the capacitance effects based on the geometry and how you choose your system. We can measure the charge of the test mass, right? But our electric field potential, we can calculate once we measure the charge, as well as we know what the capacitances are in our system. So this updated measurement system to use UV light, pulse UV light, is more easily automated, is faster, and more accurate than the method that was used on LISA Pathfinder. So this was the result of the experiment where the test mass charge was measured over time, and the phase of the UV light that was shown on it, the phase also changed through 360 degrees for a number of cycles. So you can see this is the phase of the test mass of the UV light changing over time. And as the phase changed, the charge of the test mass changed. And so you can see what the amplitude of this wave is basically backs out what electric field is present such that the test mass having a charge that's varying does respond to this. So for the single point measurement, an existing presence of about 325 millivolts was measured. And another test was done to kind of verify this result, since this was just done over the matter of 3 hours, which was significantly shorter than what was done on LISA Pathfinder to make a similar measurement. So to verify that this was indeed truly the amount of the electric potential, an additional delta X potential was applied and repeated 5 times to kind of generate this linear curve. And the y-intercept of this curve was determined to be 331 millivolts, which is pretty close to the amount of error that was done in the single point measurement. Okay, so I've talked about modeling work that was done to understand the gravitational reference sensor and the charge buildup on it. Talked about some ground testing work that was done to understand existing electric fields that we want to cancel out in order to keep our measurement really low, and some advanced methods that were being tested on the ground in order to verify that it could work in space. And the last step of validating the system that we worked on for the LISA mission was what we call the charge management device, or CMD. The goal of this charge management device is to house and command the UV LEDs that are necessary to do the charge control. And the charge management device contains all of the necessary electronics and the UV light sources to provide UV light to the system. So here in these graphics, you can kind of see the redundancy system of the LISA mission. So since this mission is quite large, and it needs to, it has a lifetime of 4 years plus a hopeful 6 years extension. So the hope is that LISA will be able to fly for 10 years. It's going to be away from the Earth, so subject to more radiation, and thus we have to make sure we build in some redundancy and design our electronics for the space environment to last as long as possible. So basically, full duplexing was incorporated in all the elements. We have the UV light sources, and only 3 UV LEDs are needed per gravitational reference sensor. Each spacecraft has 2 because of the 2 telescopes on each end of the spacecraft, as you saw. So the endpoints for the interferometry of each arm has its own gravitational reference sensor. And so only 3 UV LEDs are needed for each gravitational reference sensor, but some duplexing was involved so that if some LEDs go out, you can use other ones. We have the current driver here. Again, there's a mean and redundant with full cross-strapping, and then there's a power board that takes the 50-volt spacecraft bus voltage and brings it down to the voltage rails that our current drivers need, as well as control to be able to command the UV LEDs at the desired power and phase, and then also measure back all of the telemetry data to the spacecraft bus. So this whole UV light unit, or ULU, was developed in lab at a university, being the primary. Around TRL5 is when we got a partner involved, but this was all done in-house in an academic lab. So kind of what this technology development looked like for the UV light unit was we had the TRL3 charge management device was a very analog manual proof of concept, which you can see the picture of here. This basically had one UV LED that was commanded, and it basically used analog inputs and not digital inputs to be able to command what the phase of the light was, and what the amplitude, what the power was, and everything like that. So a big step was done to transition from TRL3 to 4, which incorporated digital control, a user interface to command the UV LEDs, an optical mechanical design to run 3 UV LEDs. And although this didn't worry about having space qualified parts yet, it incorporated a lot of the functionality that was necessary that would be kind of brought through. So this achieved TRL4 distinction by the NASA Review Board, and then TRL5 was developed with a direct path to flight, starting to think about the radiation equivalents for the electronic chips, and designing the package such that it would fly in space, having the full redundancy, as you saw in the previous graphic. Basically, one unit here, as you see here, it's in TVAC testing, is able to drive up to 12 UV LEDs. And the TRL6 charge management device looks very similar to this picture. We partnered with a small company called Fibertech, to help with kind of bringing the technology from TRL4 to 5 and 6. And the total lifetime of going from TRL3 to TRL6 took about 5 years. And again, like I said, this was all done in a university lab environment, and a lot of dissertations were developed based on this work, which is pretty cool. Okay, I don't have that much time as we are approaching 2:50. And so I might need to skim through this topic a bit faster than I would have liked. But the other topic I want to talk about for hardware development is some work that we've been doing here at Virginia Tech to develop EMCCDs, or electron multiplying charge coupled devices, in space. So this type of device is pretty new for spaceflight applications. It's been baselined on a number of suborbital missions, such as Fireball 2, which is a balloon UV spectrograph. The EMCCD is going to be the primary detector for a coronagraph instrument that's going to be in the Nancy Grace Roman Space Telescope. And you can see a picture of a subsystem involving the EMCCD here, kind of hanging off to the side with its supporting electronics here. Oh, I'm not pointing. Here's the EMCCD detector off to the side from its supporting electronics. And there's some motivation to develop this technology for a CubeSat form factor, which is what we've been working on here at Virginia Tech. So to introduce the topic, this is a technology development mission done through the NASA ROSES Heliophysics Technology and Instrument Development for Science. And the science mission of this project is to investigate the coupling of the middle and the upper atmosphere by space weather through measuring nitric oxide in polar night. So in the poles, when it's nighttime in the winter for a long time, it builds up for long enough so that it can actually be transported downward lower in the atmosphere and destroy the ozone layer. So this mission these measurements have been done on sounding rocket platforms that Virginia Tech has been involved with through the Polar Nox programs with Space ET Director Dr. Bailey. And however, these rocket missions really limit us to make these measurements at one location at one time under a particular set of atmospheric conditions. And there's a desire to potentially sample this over the course of a full season or potentially over the course of a few years that a CUBE satellite type mission could afford us doing that in a cheap way. So you can kind of see the programs. We're in year 3 right now of this program. And the goal is to kind of develop this technology, do some radiation testing, instrument characterization, all things that we can do on the ground in order to mature the camera system and the concept of operations to TRL-6. So because I'm running short on time, I'm going to skip through some of these technical slides. So to summarize, basically, some work was done by a student of ours, Nicholas Jones, to basically target some stars that would be good candidates for this measurement, as well as some extensive testing development was done to model the EMCCD in MATLAB, and so that we can run through different mission scenarios to kind of understand all of the effects of noise and stuff. Again, being able to do as much as we can in the simulation environment to validate that things will work when in flight.
I will, as you're transitioning, Nick, I think, presented on that at a Space ET summit.
Yes, he did. Yes, so if you want to learn more about this mission, yeah, Nicholas has done a lot of work and it's in his thesis, and you can go check out his talk on that. So there's also extensive instrument development that we've been doing in the lab to bring this technology up to TRL-6 and kind of prove that this is a valid mission, that we're going to be able to do the science that we propose that we can do through this measurement. So this is kind of the order of events. There's a target star that that's attenuated by the atmosphere based on the concentration of nitrous oxide. There's a UV filter to only get the signal in the wavelength we care about, some optics that we're procuring from our company partner, Lawrence Livermore National Lab. And then we have our detector that measures that amount of light from the star, and the camera electronics that are able to read out the sensor in this electron multiplied manner. So here's some pictures of the instrument development that we've been working on thus far. You can kind of see here, this is what we're doing in the lab, involving a custom dewar that we've made to put the sensor under vacuum, but also cool it down to the required -85°C necessary to make to be able to do our precision low light measurement. And we've also been doing some preliminary work to model out in CAD where everything's going to fit in a 6U spacecraft. Can we get everything to fit that's necessary for the mission to be successful? And if so, where would it live? What would the orientation be for making the measurement? So currently, we're doing laboratory tests to characterize and validate this delta-doped EMCCD detector. This picture on the far right, we got yesterday. We've just been able to finalize the procurement of the custom dewar and are working on getting our vacuum system airtight and able to pump down to low pressures. And we also have a optical breadboard that's going to be able to allow us to explore different camera modes that might be necessary to make the stellar occultation measurement. And we have some issue with the electronics running the sensor. They're overheating. And so we have to incorporate an additional coolant system. Not only do we have to cool the detector, but we also have to cool some of the electronics that run the detector. So we're incorporating that. And we're also going to do some radiation tests and do performance tests pre and post radiation tests. And yeah, basically the idea for this is we're hoping to fly this in a CubeSat, 6U CubeSat that Virginia Tech would lead. There is another step of funding that we're hoping to get that will help us to develop the technology and resolve some of these issues. Like, for example, the electronics that are too warm, and verifying all of all the different camera modes that we need. And we're hoping to get a flight opportunity in the heliophysics division of NASA to get this to fly. So I apologize for being a little rushed there at the end. Thank you very much for your time. And if you have any questions, I can answer them here in the few minutes we have. Thanks.
Any questions either in the room or online?
I have one question.
Yeah.
Can you go to the slide where you show the yield curves?
Where I showed the
yield curves, the number of electrons yield per photon.
number of electrons per photon.
The short noise.
Okay. Let's see. Oh yeah. Okay. The frequency. This one.
Yeah.
Okay.
No, not this one. It was a few slides before. I guess one more slide. Yeah, this one. Yeah, here I was a bit confused about the apparent yield, which is the number of electrons produced per photon, right?
Yes.
So what is the significance of a negative field here? Negative yield here?
This negative slope.
When the values are negative.
So basically, this is telling us that when the test mass potential is negative, our apparent yield, so the amount of electrons per photon that we can eject is positive. And the higher the test mass potential, the more electrons we can eject per UV light power. So basically, what happens is the light only allows the electron to leave the surface, but it doesn't necessarily push that electron to go to a different surface. So if the test mass potential is low enough, then basically there's not enough presence of a difference to move the electron from the test mass to the housing. So it'll eject the electron, but the electron will just go back to the test mass, if that makes sense. So that's why, like, at higher potentials, positive or negative, then you have different apparent yields.
So this is for a positive potential, the electrons they are ejected, but they don't go as far beyond, right? Is that right?
Yeah, I guess closer to zero, when the test mass potential is closer to zero, they don't go as far. But for when it's farther away from zero, then they have more energy to go farther because of the difference of the test mass potential to the ground of the spacecraft. Yeah, of course. And the sign difference might be because of it's electrons, so it depends on the direction of charge changing. So if it's charged if the test mass potential is negative, then you need to eject electrons off of it to bring the charge positive. And so that's why you have a positive number of electrons.
Yeah, thank you.
Yeah, thanks for the question.
I've got a question, Sam, if you can hear me.
Yes, I can.
Great. I think my question is most relevant to slide 13, I think. There you go. Yeah. So I'm curious about, the gravitational wave perturbations that you're trying to measure are, of course, really, really small, right? Yes. I mean, that's what makes it hard to do. But I guess I'm not sure that I'm getting as much out of your curves on this slide as maybe I could if I can convince you to explain it a little more to me. I'm wondering, how does the magnitude of the perturbations that you want to measure that represent a real gravitational wave, how do those compare to things like thermal noise in your electronics, the perturbations from this electrostatic charging issue, the 70 millivolt, got to contain it so it doesn't charge up the mass that's suspended. Perturbations from ACS, drag-related torques, radiation pressure variations when you pass into the shadow of the Earth. How do those compare as a level of magnitude? I'm trying to figure out whether you're really looking for a needle in a haystack here, and you really got to do a really fantastic job of filtering out all these other sources, or is it not that bad? So you can give me a feel for that?
Yeah, for sure. Well, something to consider is that the orbit is going to be trailing the Earth in orbit around the sun. So the effects of like being in shade and stuff doesn't really affect this constellation. It's not like a Earth orbiting
Okay.
constellation. So that's one factor. But I think to answer your question, so you can kind of see here this black curve. This is the total, this is the noise floor for the LISA mission. And that curve comes from a summation of all different subsystems, the amount of noise that it's able to contribute. I believe that this upper end, the higher the higher frequencies is a function of, I have the graph somewhere, so I'm trying to remember, but it's a function of the orbit itself. It's like how accurate you can get the inertial sensing. But
Okay.
since we care about, also there's some other things that we're doing at higher frequencies, because we don't care about the gravitational wave signals at high frequencies. We care about them at these lower frequencies. So as seen here, this pink curve is the amount that the gravitational reference sensor team has been given of, you cannot exceed this amount. This is your budget based on the total mission budget of noise. And so there's other curves that you could draw in that when you sum them up, you get the black curve. So I'm not as familiar with exactly what those are, but the black curve basically captures what all the systems together sum up. Now, on LISA Pathfinder, we were able to get to the requirement of this pink curve, but we were hitting this pink curve. Basically, we were saying this is the noise. And that's part of the reason why it's what's given as the noise limit for LISA, because it was confirmed that you could get to this on LISA Pathfinder. However, we've developed a method to keep the charge really close to zero at all times. Before on LISA Pathfinder, they'd let the charge go up and they would shine a bunch of light in at once, and they would bring the test match back down to the -70 millivolts and then left to charge up again. But that caused this red curve, basically. That depends on the DC value of the charge. It basically brought it up to where it's really close to this pink curve. So that's kind of where the trade-off is. So this basically is validating the fact that not letting the charge wander, keeping it really close to zero at the course of time, really significantly, like a factor of 6 below what that subsystem is given. So that might potentially affect the overall mission budget to bring this black curve down lower, or afford some other subsystems to, if it's noisier, maybe the noise due to the GRS is less than what they've been given. So it's a trade-off.
Well, that explains it. I think I have a better understanding now based on the electrostatic effect that you were talking about and the need to cancel that out. But I guess I'm still a little unclear on other sources of noise, like just thermal noise in your electronics and other spacecraft induced effects that are maybe very small. Are those either in such a different frequency range that it doesn't matter to this measurement, or is it really possible to keep all those other perturbations so small that these gravitational waves will be measurable and proven through those measurements? I guess I just don't have a relative feel for what the different noise levels are for all the factors that might affect the measurement.
Yeah, I don't know if I have a good sense for that either, for all the factors that make the mission possible. But I do know that a lot of systems will make sure that things are above 1 hertz of
okay.
So they'll be noisy, they'll be going crazy, right? As long as it's above 1 hertz, they don't care.
I got it. Okay.
The mission doesn't care. So yeah, things are going to be moving. They're going to have a lot of forces, but as long as it's not in the frequency band that you care about for the science measurement. So that, I think, helps it be actually successful at these lower frequencies.
Yeah. Okay. That it'd be nice if the graphic somehow could explain that, but we can talk about that later. But yeah, that's helpful, because I kind of thought that might be the effect, because you're looking at such low frequencies here. And most other things are happening faster than that. So, okay, thanks. That clears it up.
Yeah.
We're about 5 minutes over. So any other quick questions before we break? otherwise, yes, what you said you had another, this is like sort of a preview for a seminar that you're doing. Is that more open or on Friday?
Yes, on Friday. I think it's open for anyone who wants to attend, but AOE is hosting it or whatnot. So
Okay.
yeah, it's Friday at 10 a.m.
Yeah. It's a little bit earlier, but
Yes, in the morning. So
yeah. But otherwise, round of applause. Thank you very much
thanks
for
everyone.
your seminar. And I saw Leon, there was nothing else in the chat aside from Leon had to drop off a little bit ago.
Okay.
So yeah, and feel free for the people here in the room. Please take a donut, or not a donut, the cookie. Thank you. And we'll be in 2 weeks. So otherwise, students, enjoy your spring break next week.
Thanks, Kevin.